this will wrap up the chapter that we've been talking about as far as the chapter started out with how to draw a sample wisely, observational studies, the difference between those and experiments, and then the last couple of sets of notes have been about how to design experiments specifically. Now the purpose of all of the things that we've been talking about is so that we can eventually, hopefully, if we do all of those things the right way, we can draw conclusions. Maybe draw some cause and effect inferences. Things like, and I'm sorry for the typo there, the U.S. Census Bureau surveys 60,000 households monthly. The goal is to use these randomly selected households to estimate, that should say the, percentage of unemployed individuals in the population. Or scientists perform an experiment that randomly assigned 21 volunteer subjects to one of two treatments and then saw if like sleep deprivation causes a decrease in work performance. So one of these is an observational study and one is an experiment. And actually both can be used to find causation, and we'll talk about that in just a second. Inference for sampling. When members of a sample are selected at random, we can make inferences about the population. That's huge. I'm going to make sure to emphasize that a lot throughout the notes. If you're reading a scenario and it says that the sample is selected at random, then you are allowed to make inferences about the population that the sample is pulled from. Think of that teacher conference problem that we all a lot of us struggled with on that first quiz. If you want to know about everybody across the state, but if you only pull a sample from the population of those at the teacher conference, that's your population you can make inference about. As long as you are randomly selecting, then you can make inference about population. If you run into a situation, a lot of times on experiments, people volunteer to be involved in an experiment. If you read that volunteers are where they're getting their individuals, then you can't draw inferences about population, just those individuals. Okay, that said, results from samples won't exactly reflect the truth about a population. For example, a random sample of U.S. teens shows that 26% reported more than 8 hours of screen time a day. That's a random sampling of all U.S. teens. It would be surprising if we could actually collect all the data and get exactly 26%. So it's just an estimation. And that happens because of something called sampling variability. And what that is, that refers to the fact that different samples of the same size from the same population can produce different estimates. So it kind of helps us estimate when we draw a sample, but it's not going to be exact, and that is due to sampling variability. Our answers, our estimates, are going to differ or vary from sample to sample. Right here, this is kind of just a little blurb I want to make sure that I have in your notes. Larger samples tend to produce more accurate results. Larger samples produce estimates that are closer to the truth. Estimates from larger samples are more precise. So you may read on a multiple choice question, it might tell you all the information and say, how could this be redesigned, this experiment or this observation be redesigned to be more accurate? If one of the answer choices is, increase the sample size, that would be what they were looking for there. So the bigger your sample, the more accurate your results. We've kind of talked about that since the first day of class. Let's look at this problem really quickly if you want to cover up the solution or just ignore it. You're going to have a test question very similar to part A. How much do National Football or NFL players weigh on average? In a random sample of 50 NFL players, the average weight is 244.4 pounds. So out of all the football players, I randomly select 50 of them. I get all their weights, I average them together, and in that specific sample, the average weight is 244.4. A says, do you think that that is going to be the true average of the entire population of NFL players? So you're going to have a test question very similar to that if you want to make a note. It's multiple choice. And you probably know, no, that's not going to be the exact average if I were to take the weight of all the NFL players due to sampling variability. Let's see what the answer says and how it's worded. No, different samples of size 50 would produce different averages of weight. So that pretty much sums it up. Part B says, which would be more likely to give an estimate closer to the truth, a sample of 50 or a sample of 100? Sample of 100. Explain is just, well, estimates tend to be closer to the truth when the sample size is larger. Larger samples give us better estimates. Pretty straightforward there. Inference for experiments. What can we infer? Well-designed experiments, again, well-designed is those 4 components that we talked about in 4.3. Well-designed experiments allow for inferences about cause and effect, but we should only conclude that changes in the explanatory variable cause changes in the response variable if the results are said to be statistically significant. What does that mean? If you're reading a problem and it says something happens and it's the numbers in the experiment show that it's statistically significantly larger or something like that, what that means is the observed results are too unusual to be explained by luck or chance. So there's something going on there. We can draw some sort of conclusion if our results are statistically significant. Now I'm going to skip a lot of this page, okay, because as I was looking back through at my notes, I just don't think that a lot of this is necessary. I feel like some of you would get bogged down in the actual numbers themselves. But here's what happened. Mrs. Lewis's class performed this caffeine experiment where some of us got caffeine, some of us didn't. We compared the increase in pulse rate. So you've got this table of data. This is where you really don't worry about the numbers themselves, okay? And it turns out that on average, those who drank caffeine, their pulse rate increased by 3.2. No caffeine, theirs only increased by 2. So the difference of that, the difference in the averages of caffeine versus no caffeine is 1.2. And I want to know, is that unusual that that happened? Is it statistically significant that that happened? Because if it is, I might be able to say, all right, now I'm pretty sure that caffeine causes an increase in pulse rate. Well, it turns out, and we will go over this in some upcoming chapters, so don't get too worried about what's going on in this dot plot here. But it turns out if we perform this experiment, this caffeine experiment, lots and lots and lots of times, 100 different times, that answer that we got in Mrs. Lewis's class of 1.2, well, that ended up happening this many times out of 100. 19 different times that happened. That's 19% of the time that this experiment gave results like what we got, or even higher than that. There was even a larger difference. It turns out in the world of statistics, that is not very significant. That is not statistically significant. Our cutoff is about 5%. Anything that happens more than 5% of the time is really not that rare. This happened 19% of the time, so it's certainly not statistically significant. All that is to say, if you do get results that aren't statistically significant, you can't really draw any sort of conclusion or make inference about cause and effect. Now, I'm thinking about the test that you're going to have next time. You're going to have test questions that say explicitly that the results are statistically significant. So what do we do with that? Turn the page. This is the most important page of your notes. This little box of information and this little table say the exact same thing. Actually, all of this says the same thing. You decide what is easier on your eyes. But we're talking about the scope of inference. You're even going to have a little part of a free response question on your test about scope of inference. The scope of what you can infer comes down to two questions. Can I make an inference about a population based on the data that I collected? Well, so can I make an inference about the population? Yes, as long as individuals are randomly selected. So that has to do with your sampling method. If you read in a problem, once again, if you read in a problem that the participants are randomly selected, then you're allowed to make inference about the population. If they're not, let's say they're volunteers, you can only make inferences about people like that. So I'll explain more in just a second. The second main question when you're trying to infer is, can I make an inference about cause and effect? Is there some sort of cause and effect relationship happening? This is really easy. The answer is yes, as long as you read that individuals are randomly assigned to treatments or groups. Now, if they get to choose their treatment, or it doesn't explicitly say that we, somehow use a random number generator, or we draw names out of a hat to randomly assign them, if they're not randomly assigned, then you can't make an inference about cause and effect. So again, the two parts are inference about population, inference about cause and effect. This little box sums it up for you. Random selection of individuals allows for inference about population. Random selection of individuals lets you make inference about population, that the individuals were chosen from. Random assignment of individuals to groups allows for inference about cause and effect. That says the same thing that numbers 1 and 2 say up there. This little table is my favorite because, as long as you're comfortable reading what's going on, this sums it all up in a nice little table form. Were individuals randomly assigned? Were they randomly selected? And then it'll just take you to, you answer that yes or no, and it takes you to the inference. Let's say I'm reading a situation and the people in my experiment are volunteers that I randomly assign treatments to. Volunteers, randomly assigned treatments. Were they randomly selected? Yes or no, if they're volunteers? No. Okay. And then if I randomly assign them to treatment groups, then that's a yes. So here's what I would be able to write like in a free response with context. Okay. Just writing these wouldn't cut it. Inference about the population could not be made because individuals are not randomly selected. But inference about cause and effect can be made because individuals are randomly assigned to groups. And again, when you're writing a free response, context is so important. That will get you that 5 on your AP exam if you're always putting it back in context about what's going on in the problem. Let's look at an example of this. Researchers at the University of North Carolina were concerned about the increasing dropout rate in the state's high schools, especially for low-income students. Surveys of recent dropouts revealed that the students kind of started to lose interest in middle school because they didn't see a connection between what they were learning in school and their future plans. So to change this perception, researchers developed a program called Career Start. And the main idea of the program is that teachers would show students how the topics they're learning could be applied to specific careers. So that's what's going on. To test the effectiveness of this program, the researchers recruited 14 middle schools in this particular county. So 14 middle schools in this particular county were chosen to participate. 7 of the schools determined at random used the program along with what they were already learning, And the other 7 schools just followed what they were already learning. So those are the 2 treatments. Researchers followed both groups of students for several years, collecting data on attendance, behavior, test scores, engagement, and whether or not they graduated. Here are the results. Students at the schools who used Career Start generally had significantly better attendance, fewer discipline problems, earned higher scores on their test, and reported greater engagement, and were more likely to graduate. Okay, all of that. Results. Great. Keyword. It doesn't say statistically significant, but it says the word, it's significant. So look at this one little question. What conclusions can we draw? So you need to address both of these parts. So let's kind of break this down. Were schools, now I just noticed something. Right up here at the top of the paragraph, we're concerned about the dropout rate of the entire state's high schools. The entire state. And don't get too hung up on the fact that middle schools were a part of this, okay? We're trying to see about the high schools here. From the entire state. The 14 schools that they chose, you guys, did they choose them at random from across the state? No, they chose them all from the same county. That doesn't mean that everything falls apart and this is a terrible experiment. It just means we can't make inference because the individuals were not randomly selected. We can't make inference about the population of high schools across the state. We could only make inference about schools like this. Now let's read how they wrote that down here. That's at the very, very end. The results apply only to schools like these because the schools were not randomly selected. So that's what that sentence addresses. That's part of the conclusions that we can draw. Now, the other question is, out of those 14 schools, did they randomly assign treatments to the groups? They did. It says 7 of the schools determined at random used Career Start. So they randomly assigned these schools to the program. Because of that, that means that individuals are randomly assigned, then we can make inference about cause and effect. Let's see how we would write that in context. And that's what the beginning of the paragraph says. Because treatments were randomly assigned and the results were significant, we can conclude that using the Career Start curriculum, this is the context part, caused better attendance, less discipline problems, higher test grades, greater engagement, and increased graduation rates. So don't just say we can make inference about the cause and effect, but not about the population. That would give you partial credit on a free response, but they want it always to be in context. Okay, that's probably the most important page of the notes. When we flip over to the back, I'm going to zoom through this. We've talked about experiments so much this chapter that it might seem like observational studies really aren't that useful. They totally are. They can be. In some cases, it's not practical to perform an experiment because it's not really ethical. Like if I wanted to see, does going to church regularly help people live longer? Going to church regularly help people live longer, or does smoking cause lung cancer? I can't take some volunteers and make them smoke cigarettes to see if it causes them to get cancer. That's not ethical. I can't perform an experiment. I would just have to observe what's going on and maybe draw some conclusions from that. Now there are some specific things or criteria for establishing causation when you can't do an experiment. And in italics there, you'll just see kind of this relating back to the whole, we're pretty sure that smoking cigarettes causes lung cancer, so it just gives an example of each of those. So the association has to be really strong. There has to be an association, It has to be really, really strong. Like the association between smoking and lung cancer. The association, because, and you'll see association a lot in here, that doesn't necessarily imply causation, but if it's strong and it's consistent, then you're on the right track to being able to draw some conclusion about cause and effect. Larger values of the explanatory variable are associated with stronger responses. For example, people who smoke more cigarettes per day or who smoke over a longer period of time get lung cancer more often, and people who stop reduce their risk. So that's showing that larger values of the explanatory variable are associated with stronger responses. Alleged cause precedes the effect in time. Lung cancer, which is the effect, develops after years and years of smoking, which is the cause. So cause comes before effect. And lastly, the alleged cause is plausible. One of the ways we know that this is plausible is experiments with animals have shown that tars from cigarette smoke do cause cancer. You're not really going to be tested on any of these things, but I just want to give mention and give credence to the fact that observational studies can be useful to draw cause and effect conclusions if they meet specific criteria. Lastly, this is not even on your AP exam, but I think that it's kind of important talking about data ethics. All planned studies have to be reviewed in advance by an institutional review board. Institutional, hang on, let me wipe that out. So before you can do a study, it has to be reviewed by an institutional review board. And they're charged with protecting the safety and well-being of the subjects. All individuals who are in a study must give their informed consent. When you go to college, if you're ever asked if you want to participate in a psychology study, do it. It's fascinating, it's interesting. There's this little form where you give your consent to be a part of that. But it's one of my favorite memories from college. It's just interesting. And all individual data must be kept confidential. Only statistical summaries can be made public. I wouldn't be able to post a person's name and their income. I would be able to post like the average income of a specific area or something like that, the summary, but not individual data. So that pretty much wraps up the chapter.